1 by 5, 2 minus 2 by 5. This is exactly the inverse, this is exactly the standard matrix for T inverse. And now from the standard matrix we can easily write down the T inverse xy, that is equal to 2x plus y divided by 5, and then minus will be common, 2x plus y divided by 5, and then x minus 2y divided by 5. Okay, so question 1-4 is complete now. Fifth part of the question 1. Find the coordinates of a polynomial p, that is equal to 5 plus 11x plus 2x square relative to the basis s is equal to 1 minus x, 1 plus x, 1 minus x square of P2R. This means set of polynomial of 2 degree, right, on real numbers. So 5 plus, we have to find the coordinates of a polynomial. This is our polynomial p. So 5 plus 11x plus 2x square, that is equal to c1 into 1 minus x plus c2 into 1 plus x plus c3 into 1 minus x square. That step here I don't written here, but you can try to understand. C1 into 1 minus x plus c2 into 1 plus x plus c3 into 1 minus x square. So the constant part is c1 plus c2 plus c3, then the x, the terms of the part which contains x, that is minus c1 plus c2, okay, and the last part is minus c3 x square, because we have only one term which have x square, so minus c3 x square. Now comparing left and right hand side part, we get c1 plus c2 plus c3 is equal to 5, minus c1 plus c2 is equal to 11, and minus c3 is equal to 2. So c3 is equal to minus 2. Okay, put the value of c3. c2 is equal to 9 and c1 is equal to 2. Okay, c3 is equal to 2, so put the value of 2 here. So we get c1 plus c2 is equal to 3, c1 plus c2 is equal to 3, and here minus c1 plus c2 is equal to 11. So then add that two equations, we get 2c2 is equal to 4, right? So finally we get c2 is equal to 9. Okay, minus c3 is equal to 2, so c3 is equal to minus 2. Put c3 is equal to minus 2 here, so we get c1 plus c2 is equal to 7, correct? c1 plus c2 is equal to 7, and here minus c1 plus c2 is equal to 11. So when we add this to equation, we get 2c2 is equal to 18, so c2 is equal to 9, and put the value of c2 here, we get minus c1 plus 9 is equal to 11, so minus c1 is equal to 2, so c1 is equal to minus 2, right? Question 1-6. Determine the algebraic multiplicity of A, where our matrix A is 0 1 0 0 0 1 1 minus 3 3. The characteristic equation is determinant of A minus lambda I, that is equal to minus lambda 1 0 0 minus lambda 1 1 minus 3 3 minus lambda. So the characteristic equation is determinant of A minus lambda I, that is equal to minus lambda into minus 3 lambda plus lambda square plus 3 minus 1 into minus 1, that is equal to 0. So lambda cube minus lambda into lambda square, that is lambda cube minus 3 lambda square, lambda cube minus 3 lambda square plus 3 lambda minus 1, that is equal to 0. So lambda minus 1 cube, finally this is equal to lambda minus 1 cube, that is equal to 0, and lambda is equal to 1 1 1. So the algebraic multiplicity is 3 because this 1 is an eigenvalue and 1 occurs 3 times. So that's why the algebraic multiplicity of 1 is 3. If you want to find the geometric multiplicity of particular eigenvalue, then we have to find the first of all we have to find the eigenvector corresponding to that eigenvalue, and then see how many eigenvectors we have corresponding to that particular eigenvalue. If suppose we have only one eigenvector, then the geometric multiplicity of that eigenvalue is 1. If we have two eigenvector corresponding to that eigenvalue, then the geometric multiplicity of eigenvalue, that particular eigenvalue, is 2. So that depend upon the eigenvector, but the algebraic multiplicity is depend upon the how many times eigenvalue occurs, right? So algebraic multiplicity means as an eigenvalue how many times that eigenvalue occurs, and the geometric multiplicity means that eigenvalue corresponding to that eigenvalue how many eigenvector, right? So that is, so clearly the algebraic multiplicity is always greater than geometric multiplicity. Okay, next question, question first 7. Let W is equal to span of this two vector 0 1 0 minus 4 by 5 0 3 by 5. Express W 1 1 1 in the form W is equal to W1 plus W2, where W1 belongs to W and W2 belongs to orthogonal of W. So V1 is equal to 0 0 1 0 and V2 is equal to minus 4 by 5 0 3 by 5. So projection of W, that is equal to inner product W V1 with V1. So inner product of W with V1, that is equal to 1 1 1 into dot 0 1 0, that is 1 into 0 0 plus 1 into 1 1 plus 1 into 0 0. So we get 1, and then inner product W V2, so that is equivalent dot product, that is 1 1 1 minus 4 by 5 0 3 by 5. So we get minus 4 by 5, then 0 plus 3 by 5, so minus 1 by 5 V2, correct? So 1 into V1 minus 1 by 5 into V2, 1 1 1 0 1 0 into V1 plus 1 1 1 minus 4 by 5 0 3 by 5 into V2. So that is 1 into V1 minus 1 by 5 into V2. Now we have to find V1 minus V2 by 5. So that is W1, call it W1. You can see V1 is 0 1 0 and V2 by 5. So that is 0 plus 4 by 25. So that is 4 by 25. Then 1, right? Here 0. So 1 minus 0 0, and then 0 minus 3 by 25. So minus 3 by 25. So W1 is 4 by 25. 1 minus 3 by 25 belongs to W. Now then projection of W over the orthogonal of W, that is equal to W minus projection of W, that is 1 1 1, right, minus 4 by 25 1 minus 3 by 25. So that is 21 by 25 0, 1 minus 1 0, and then 1 minus 1 plus 3 by 25. So that is 28 by 25. So 1 1 1. So W2 is equal to 1 1 1 is equal to, we can express W1 plus W2, where W1 belongs to W and W2 belongs to the orthogonal of W, right? So here we complete the question number 1. Next question, question 2. A. First part. Verify whether the following set of matrices are Hermitian or skew Hermitian or neither. Give reason. So what is the meaning of Hermitian and skew Hermitian? If A is a Hermitian matrix, that means A star, where A star is transpose of A complement of A, right? So complement of A means in that matrix all the complex number we have to complement, right? So C plus ID becomes C minus ID, C minus ID becomes C plus ID, you can see. So A is equal to, this is our A, matrix A, right? A bar, that is equal to complement of A, that is A, C minus ID, C plus ID, B. Now transpose of this matrix, so definitely the transpose of this matrix is again become A. So A transpose of A bar, that is equal to A, C plus ID, C minus ID, B, that is equal to A. So definitely A is Hermitian. Now to check that A is skew Hermitian matrix, this matrix, second part, that is a skew Hermitian matrix. 2i, 1 plus I, minus 3 plus 2i, minus 1 plus I, 0, 2 minus I, 3 plus 2i, minus 2 minus I, and minus 3i. Is it skew Hermitian matrix? Let's try to check. B bar become minus 2i, right? 1 minus I, minus 2i, okay, 1 minus I, minus 3 minus 2i, minus 1 minus I, 0, 2 plus I, right, 3 minus 2i, minus 2 plus I, and 3i, correct? So the transpose of this matrix, now interchanging the row and column, transpose of the given matrix means we have to interchange row and column. So minus 2i, 1 minus I, minus 3 minus 2i, then minus 1 plus, right, this is minus 1 plus I, 0, 2 plus I, and then 3 minus 2i, minus 2 plus I, 3i. So that is equal to minus will be common from the matrix. So we get, you can see 2i, 1 plus I, minus 3 plus 2i, minus 1 plus I, 0, 2 minus I, then 3 plus 2i, minus 2 minus I, minus 3i, right? That is equal to minus B. So this B is a skew Hermitian matrix, because we prove that the transpose of the transpose of the complement of B, that is exactly minus B. You can see from this step, so that's why B is a skew Hermitian matrix. Okay. Next question, question 2, second part. Reduce the following matrix to reduce row echelon form. Here we have 4 cross 4 matrix, right? And this question was asked in 3 marks. As I told you before that how to convert a matrix into a reduced row echelon form. So we are multiplying first row. This is our matrix A, right? We have to convert this matrix into a reduced row echelon form. So that's why we are multiplying first row with 2 and add into the second row, and we are multiplying first row with minus 1 and add into the third row. So the first row is 1, 2, 3, minus 1. The second row is 0, 3, 3, minus 3. The third row becomes 0, minus 2, 2, and the fourth row is as it is 0, 1, 1, minus 1. Then we are multiplying fourth row. We are multiplying fourth row with minus 3 and add into the second row. So the second row become 0, right? Because the second row is exactly the multiplication of the fourth row. You can see 3, 3, minus 3. So whenever we are multiplying fourth row with minus 2 and add into the second row definitely becomes 0. And similarly the third row is exactly the multiplication of the fourth row with minus 2. So when we multiply fourth row with 2 and add into the third row becomes 0. Then we are interchanging the second and fourth row, okay, and so finally we get this matrix, and then we have to convert reduced row echelon form. So this is our leading entry, below that leading entry is 0, this 2 are 0 row, third and fourth row are 0 rows, both are bottom of the matrix, but this is our leading entry. Below that leading entry we have already 0, but above that leading entry here we have to make 0. So that's why we are multiplying second row with -2 and add into the first row. So finally we get this matrix 1 0 1 1 0 1 1 -1, and then the other two rows are 0 rows. So this is a matrix which we convert a reduced row echelon form. This is our reduced row echelon form matrix. So here we complete the solution of this question paper up to question number 2. Thank you. Have a nice day. Oof.